In this video, which is a continuation of the previous one, we're going to talk about how homomorphisms are determined by the values that they take on a set of generators for a group. To start with, let me remind you of the properties that we've covered so far. If phi is a homomorphism from G to H, then it has to map the identity element in G to the identity element in H, and it has to map G to the n to phi of G to the n for any G in G and for any integer n. Also, the image of a homomorphism is always a subgroup of the codomain, and the kernel of a homomorphism is always a subgroup of the domain. And if the homomorphism happens to be an isomorphism so that it's a bijective map from G to H, then its inverse function is also an isomorphism from H to G. Next, what do homomorphisms do to orders of elements? Well, if you have an element little g with finite order, then its image under a homomorphism always has to be an element whose order divides the order of G. And if your homomorphism happens to be an isomorphism, then the order of G and the order of phi of G have to be the same. Also, what we saw to be a pretty useful property, if phi is an isomorphism from G to H, then it also gives a bijection between the collection of elements of order n in G and the collection of elements of order n in H. So that means that the cardinalities of those two sets have to be equal to each other. And finally, in the previous video, we also proved that if phi is an isomorphism from G to H, then G is abelian if and only if H is abelian. And if phi is an isomorphism, then G and H have to have the same lattices of subgroups. Okay, well, in this video we're going to start by proving something which is really going to help us when we're trying to construct homomorphisms from a group G to a group H. This is property 8a, and what it says is that if your group G is generated by a set S, then any homomorphism from G to H is completely determined by the values that it takes at the elements of this generating set. What this means is that if you have any other homomorphism phi tilde from G to H, which agrees with the homomorphism phi at the point in the generating set, then it must also agree with phi everywhere else so that the two homomorphisms must be the same. This is an important property because if we can identify a generating set for the group G, then in order to understand homomorphisms from G to another group H, we just need to think about what those potential homomorphisms would do to the generators for G. It's also important that you understand the proof of this property because some of the elements of this proof are going to come up again when we're looking at examples. So for the proof, let's suppose that we have a homomorphism phi as above, and let's suppose that phi tilde is a homomorphism from G to H with the property that phi tilde of S is equal to phi of S for every S in the generating set S. Well, the fact that S is a generating set means that for any G in G, we can write G as a finite product of elements of S and their inverses. So to make that statement formal, for any G in G, there exists an n and n, and elements G1 to Gn in S, which are allowed to be repeated, together with exponents U1 to Un, which are all plus or minus 1s, with the property that G is equal to G1 to the U1 ... Gn to the Un. This is just a formal way of saying what I said before, that any element of G can be written as a finite product of elements of S and their inverses. Now think about what phi tilde does to this element G. Since phi tilde is a homomorphism, it passes through all the products here, and by property 1c, all of the UIs pop out, so that phi tilde of G is phi tilde of G1 to the U1 power ... phi tilde of Gn to the Un power. But now remember that phi tilde and phi agree on the set S. So this is the same as phi of G1 to the U1 power ... phi of Gn to the Un power. And now recombining all of these elements using the fact that phi is a homomorphism, I see that this is exactly equal to phi of G. That proves what we wanted to prove, that any homomorphism from G to H which agrees with phi on the set S must actually be the same as phi. Now, at this point, I'd like to mention something very important, and that is that when you're trying to define a homomorphism phi from one group to another, and when you have a generating set capital S for the domain, if you just randomly choose values for phi of S for all elements of that generating set, there's no guarantee that the map that you're trying to define is going to actually extend to a homomorphism from G to H. So while it is true that any homomorphism from G to H is uniquely determined by its values at that generating set, it's not true in general that every possible collection of values is going to extend to a homomorphism from G to H. This is actually an important comment, and it's a source of a lot of errors in people's work, so I'm going to try to emphasize this in the examples. As a first example of how to use property 8a, let's find all homomorphisms from the additive group of integers modulo 8 to the cyclic group of order 6. To fix notation, let's write the cyclic group of order 6 as being generated by an element x, so that its elements are the identity x squared out to x⁵. Now since z mod 8z under addition is generated by the residue class 1, We know from our property that any homomorphism from Z mod 8Z to the cyclic group of order 6 is going to be uniquely determined by its value at the generator 1. Well, now there are 6 possible places where phi of 1 could map to, but remember that not every possible choice of phi of 1 is going to extend to a homomorphism from Z mod 8Z to C6. So now we need to go through all 6 possibilities and think about which possible values of phi 1 will extend to homomorphisms from all of Z mod 8Z to C6. First of all, is it possible to have a homomorphism phi here with phi of 1 equal to the identity element? Well, if phi of 1 is the identity element, then in order for phi to be a homomorphism, for every k from 0 to 7, we would then have to have that phi of k, which is phi of 1 plus 1 plus 1 k times, is equal to phi of 1 times phi of 1 times phi of 1 k times. And since phi of 1 is the identity, that would have to be equal to the identity to the k, which is the identity. So in other words, if phi is a homomorphism with the property that phi maps 1 to the identity, then it would have to map every other element of Z mod 8Z to the identity. Now, is the map which maps everything in Z mod 8Z to the identity a homomorphism? Well, it is a homomorphism, and it's what we call the trivial homomorphism from Z mod 8Z to C6. So that takes care of that choice of phi of 1. Next, let's think about whether or not it's possible to have a homomorphism from Z mod 8Z to C6, which maps 1 to the element x. Well, here, one thing to think about is that if phi is a homomorphism, then by property 5a about orders of elements, the order of phi of 1, which is x, would have to divide the order of 1. But the order of 1 in the group Z mod 8Z is 8 because it's a generator for the group. And the order of x in the cyclic group of order 6 is 6. And 6 does not divide 8. Therefore, there's no homomorphism phi from Z mod 8Z to C6 with phi of 1 equals x. So this is an example of the thing that I told you to be careful of. Not every possible choice of where to send the generators is going to extend to a homomorphism from one group to the other. Now, just to solidify this in your mind, I'd like to give you another way that you can see why this can't happen. So let's suppose that we did have a homomorphism phi from Z mod 8Z to C6 with phi of 1 equals x. Then by property 1c, since phi is a homomorphism, we would have to have that phi of k is phi of 1 to the k, which is x to the k, for every integer k. But now think about the fact that 1 is equal to 9 mod 8. Well, that should mean that phi of 9 is equal to phi of 1. But if phi of k is x to the k for every k in z, then phi of 1 is x to the 1, and that's not the same as phi of 9, which would then have to be x to the 9, which is the same as x cubed in the cyclic group of order 6. Because of the contradiction here, we conclude again that we can't have such a homomorphism. It also turns out that we can't have a homomorphism phi with phi of 1 equals x squared x to the 4th or x to the 5th. And it's pretty easy to see why that's true using a similar reasoning, especially if you remember the formula for the order of a power of an element from our video on cyclic groups. So the order of x squared is the order of x divided by the GCD of the exponent in the order of x, which in this case is 3. And similarly, the order of x to the 4th is 3, and the order of x to the 5th is 6. In all of these cases, the orders of the images of the points don't divide 8, which is the order of 1. So by property 5a again, there's no way that such a phi could extend to a homomorphism from Z mod 8Z to C6. The only case that remains to consider is the case when phi of 1 is x cubed. So let's try to determine whether or not this extends to a homomorphism from Z mod 8Z to C6. Well, if it were a homomorphism, then by property 1c, it would force phi of k to be phi of 1 to the k, which is x to the 3k for k going from 0 to 7. And here, if you like, we can make a chart of the possible values of phi of k for all of the elements of Z mod 8z. Now, by the end of the video, you're going to have a better way to do this, but for now, you can just check directly that this does actually define a non-trivial homomorphism from Z mod 8z to C6. So that leaves us with the conclusion that there are exactly 2 homomorphisms from Z mod 8z to C6. There's the trivial homomorphism, which we know is a homomorphism between any 2 groups. And there's also the homomorphism determined by the rule that 1 maps to x cubed. Now let's try another one, and this time let's try to find all the homomorphisms phi from the symmetric group of degree 3 to the cyclic group of order 6. We know from our second video about symmetric groups that S3 is generated by the transposition 1, 2 in the 3-cycle 1, 2, 3. And as before, let's choose a generator x for the cyclic group of order 6 so that it's the collection of elements identity x out to x to the 5th. Well, since S3 is generated by these 2 elements, we'd like to get some help from the property that any homomorphism from S3 to C6 is uniquely determined by its values at the generators. And a priori, since there are 6 different places to send each of these 2 generators, there are 36 different possibilities to consider here. But learning from our previous example, we can cut down the number of possibilities significantly by using the fact that any homomorphism phi has to satisfy the property that the order of phi of g divides the order of g for any g in the domain. So it makes sense for us now to go through and compute the orders of the elements involved here, and it's not difficult to see that the transposition has order 2, the 3-cycle has order 3, and in the cyclic group of order 6, the identity has order 1, the elements x squared and x to the 4th have order 3, the elements x and x to the 5th have order 6, and the element x cubed has order 2. So that means that any homomorphism from S3 to C6 must map the transposition to an element whose order divides 2, and there are only 2 possibilities. And similarly, it must map the 3-cycle to an element whose order divides 3, and for that there are 3 possibilities. So now right away we've cut the total number of possibilities for this map phi down to 6. Now we can cut the number of possibilities down even further by observing at the outset here that we can't have that the order of phi of 1, 2 is 2 and the order of phi of 1, 2, 3 is 3. So let's try to see why that's true. Well, first of all, we know that the image of S3 is a subgroup of C6, and if the order of the image of S3 were 6, then the map phi would actually be a bijective homomorphism from S3 to C6, so it would be an isomorphism. But C6 is abelian and S3 is non-abelian, so they're non-isomorphic groups, and that can't happen. Now, by Lagrange's theorem, the possibilities for the order of the group phi of S3 are 1, 2, 3, or 6, and since we can't have 6, that leaves us with the possibilities that phi of S3 has order 1, 2, or 3. Remember, though, that the order of any element of a group must divide the order of a group, which means that for every g in S3, the order of phi of g must divide the order of the group phi of S3. If it happened that the order of phi of 1, 2 were 2 and that the order of phi of 1, 2, 3 were 3, then it would mean that both 2 and 3 divide the order of phi of S3. But then that would mean that phi of S3 has order 6, which we've already ruled out. So what this shows is that at least one of the elements 1, 2, and 1, 2, 3 must map to the identity element, and that rules out 2 of the possibilities from before. Now, going through the remaining possibilities, the easy one is whether or not phi of 1, 2 and phi of 1, 2, 3 could both be the identity element. And the answer, of course, is that they could, because the trivial homomorphism from S3 to C6 has this property. So, as we already knew, there's always at least one homomorphism from S3 to C6, and it's the homomorphism determined by the rules that phi of 1, 2 and phi of 1, 2, 3 are both equal to the identity element. Next, let's think about whether or not the map phi, which sends 1, 2 to x cubed and 1, 2, 3 to the identity, extends to a homomorphism from S3 to C6. So let's first of all try to do a little bit of scratch work to decide if this map were a homomorphism where it would have to send the remaining elements of S3. Of course, any homomorphism would have to send the identity to the identity. And now, in order to figure out where such a homomorphism would send 1, 3, 2, and 2, 3, and 1, 3, we need to figure out how to write those elements as products of the elements in our generating set. So 1, 3, 2 is 1, 2, 3 squared. And that means that if phi were a homomorphism which sent 1, 2, 3 to the identity, then it would have to send 1, 3, 2 to 1, 2, 3 squared, which is also the identity. How about 2, 3? Well, we can write 2, 3 as a product of the generators as 1, 2 times 1, 2, 3. And then, if phi is a homomorphism, it would have to send 2, 3 to phi of 1, 2 times phi of 1, 2, 3, which is x cubed times the identity, or x cubed. And finally, how about 1, 3? Well, 1, 3 is 1, 2 times 1, 3, 2, which is the same as 1, 2 times 1, 2, 3 squared. So if phi were a homomorphism, then it would have to send 1, 3 to phi of 1, 2 times phi of 1, 2, 3 squared, which is x cubed times the identity squared, or x cubed. Now, like I said, later in the video, we're going to have an easier way of checking whether or not a given map determined by generators in this way actually does define a homomorphism. But for now, I'll go ahead and tell you that this one does, and I'll give you another reason why. So it's not difficult in this case just using definitions to check that this map is also the map which maps any permutation to x cubed if that permutation is odd, and to the identity if the permutation is even. Well, using the fact that an odd times an odd is an even permutation, and an odd times an even is an odd permutation, and an even times an even is an even permutation, it's easy to check that this is a homomorphism. So we conclude that the choice phi of 1, 2 equals x cubed and phi of 1, 2, 3 equals the identity does extend to a homomorphism from S3 to C6. Next, how about the choice phi of 1, 2 equals the identity and phi of 1, 2, 3 equals x squared? Does this choice extend to a homomorphism from S3 to C6? Well, as before, let's go ahead and determine if this were a homomorphism, what its values would be at the other elements of S3. And here we can use some of our scratch work from the previous example. So of course, any homomorphism would have to map the identity to the identity, And since 1, 3, 2 is 1, 2, 3 squared, phi of 1, 3, 2 would have to be phi of 1, 2, 3 squared, which in this case would be x to the fourth. And similarly, phi of 2, 3 would have to be phi of 1, 2 times phi of 1, 2, 3, which would be x squared. And phi of 1, 3 would have to be phi of 1, 2 times phi of 1, 2, 3 squared, which would be x to the fourth. But now it's not difficult to see that such a map can't be a homomorphism, because, for example, 2, 3 squared is the identity. So if phi were a homomorphism, then phi of 2, 3 squared would have to be the identity, but phi of 2, 3 squared would be x squared squared, which is x to the fourth, and x to the fourth is not equal to the identity in C6. So the conclusion here is that this choice of values of phi doesn't extend to a homomorphism from S3 to C6. Finally, by an exactly analogous calculation, it's not difficult to see that the choice phi of 1, 2 equals identity and phi of 1, 2, 3 equals x to the fourth also doesn't extend to a homomorphism from S3 to C6. And so we're left with the conclusion that there are exactly two homomorphisms from S3 to C6, which are the trivial homomorphism and the homomorphism determined by the rule that 1, 2 maps to x cubed and 1, 2, 3 maps to the identity. Finally, another property which is very useful in conjunction with property 8a is that if G is generated by a set S, and if phi is any map from S to H, with the property that any relation in G satisfied by the elements S1 to Sn and S is also satisfied in H with these elements replaced by phi of S1 out to phi of Sn, then phi extends uniquely to a homomorphism from G to H. Now, this is a very good companion to property 8a when you're trying to determine the collection of all homomorphisms from one group to another. Because, like I said before, not every possible choice of phi of S1 to phi of Sn is going to extend to a homomorphism from G to H. But how do you know which ones do and which ones don't? Well, what this property tells you is that as long as any relation satisfied by the generators is also satisfied by their images, then it's going to extend uniquely to a homomorphism from G to H. Of course, that sounds like it might be something which is difficult to check in general, but it's especially useful when you have a presentation for your group using generators and relations. So when your group is given to you using generators and relations, then you don't need to try to conceive of every possible relation that could be satisfied by the elements S1 to Sn. You only need to check that for all of the relations in your presentation, they're also satisfied when you replace the SIs by the phi of SIs. If that happens, then you're guaranteed that your map phi extends uniquely to a homomorphism from G to H. I'm not going to try to prove this because it really requires you to understand in a more detailed way what a presentation for a group actually is. So we're not ready to try to see the proof yet, but this is something which you should have at your disposal because it's very useful in practice. As a final example to illustrate how property 8b is useful, let's at last prove that D6 is isomorphic to S3. As I mentioned in the previous video, this is something that we could have done before, but now that we have properties 8a and 8b, it's going to be a lot easier. So remember that a presentation for D6 is as the group generated by R and S, subject to the relations that R cubed equals S squared equals identity, and RS equals SR inverse. And now what I'd like to do is consider the map phi which maps R to the 3-cycle 1, 2, 3, and which maps S to the transposition 1, 2. First of all, I'd like to claim that this map extends to a homomorphism from D6 to S3. So in order to do that, I'm going to use property 8b. Since I have a presentation for this group, what I need to check is that for every relation in the presentation, that relation is also satisfied in S3, with the R's and S's replaced by their values under this map. So if I replace R by 1, 2, 3, then I see that 1, 2, 3 cubed is the identity element in S3. And if I replace S by 1, 2, then I see that 1, 2 squared is also the identity element in S3. And finally, for the last relation, on the left-hand side here, if I replace R by 1, 2, 3 and S by 1, 2, then multiplying these elements of S3 together, remembering that I'm working in a non-abelian group, it's easy to see that you get the transposition 1, 3. And on the right side of the equation here, multiplying together 1, 2 times 1, 2, 3 inverse, and using the fact that 1, 2, 3 inverse is 3, 2, 1, I also get 1, 3, so that the left and right hand sides here are equal to each other. Now since phi of R and phi of S satisfy all of the relations determined by this presentation, I can conclude from property 8b that phi extends to a homomorphism from D6 to S3. But now think about the fact that the order of phi of R has to divide the order of the image of D6. Since the order of phi of R is equal to 3, that means that the order of the image of this map has to be divisible by 3. And similarly, since the order of phi of S has to divide the order of phi of D6, I also see that 2 has to be a divisor of the order of this group. That means that the image of this map has to be a group of order 6, So it means that the map is a bijection, and since it's a bijective homomorphism, it's an isomorphism. So that's a very easy proof of the fact that D6 is isomorphic to S3. And it's a good example of how properties 8a and 8b can be useful when you're trying to construct homomorphisms from one group to another. Well, that's the end of this video. Thanks for watching. In the next video, we're going to start making our way towards talking about quotient groups by first talking about normal subgroups.